Now, example would be, chlorine. When somebody's talking about chlorine, it depends on what they're talking. Normally, chlorine we know is a diatomic, and so Cl2 is typically thought of as being chlorine. So we'll have these two chlorine atoms bonded together. This is the gas phase, the free to move, whichever way. So what happens when we have Cl though? What do we call Cl? We also call Cl chlorine. And so both of these are called chlorine. Well, which one is which? So sometimes what we do with Cl is we'll call this atomic chlorine, but sometimes we won't. Sometimes based on the context of the question, we'll know. So atomic chlorine or just chlorine. Okay, this would be called diatomic chlorine or molecular chlorine or just chlorine. So diatomic chlorine, molecular chlorine, because these two atom units are molecules, molecular chlorine, or just plain chlorine. So if you're not sure, you look at the context of the name. And so I think looking at the context of the name or the context of the question, we say, like, how much chlorine is in table salt? And so here, what type of chlorine are they talking about? Are they talking about Cl2, which is a green corrosive gas? No. We know that table salt. And so in this case, they're talking about how much Cl. Not Cl2. And so sometimes it's a little bit ambiguous, but sometimes you'll get a clue as to what they're talking about in the problem itself. And so it depends.
Is a Cl poisonous with CO2?
Cl,
yeah.
if you have atomic chlorine, it depends. It depends on what state it's in. For example, if it's in sodium chloride or table salt, it's not poisonous. This is what we call a stable state of chlorine, a relatively stable. It's a solid here. You can see it here. Sure. This figure was in the PowerPoint. Sorry, good. So here's a crystal of table salt. In this particular state, it is fairly stable. When you look at the chlorine, one thing about the chlorine in this particular state is it does have a negative charge here. When chlorine has a negative charge, we call it chloride. So sodium has a positive charge, we just call it sodium. So sodium with a neutral charge and sodium with a positive charge is called sodium. This is sodium chloride. However, the charge makes a huge difference, because if there's no charge, then what we're looking at is we're looking at chlorine gas. Chlorine gas is this green gas here in the flask. Chlorine, diatomic or molecular chlorine over here. And these chlorine atoms have zero charge. They're neutral. And then if we look at sodium metal, which is shown over here, This is sodium metal. Sodium metal forms a lattice, a crystalline lattice. Sodium atoms packed together, they're actually bonded together. These are called metallic bonds here. And these have no charge. And so here we call this sodium or sodium metal, which is just the formula. What is the formula for sodium metal? The formula for sodium metal is just, because how big is this crystal? It's actually pretty big here. Usually you buy sodium, it comes in these little rolls. You can cut off the piece. And so since there's no real end to it, it's called sodium metal in a solid. Now sodium metal is very dangerous metal. You don't want to consume the metal itself. If you consume the metal itself, then eventually you would die. Same thing with chlorine. But sodium and chlorine undergo a chemical reaction. The chemical reaction is shown here. It's like a combustion reaction. Do you see it burning? And in fact, it is kind of like a combustion. It's the same type of reaction as a combustion reaction. After it finishes burning, we're left with the salt crystals. And so this is quite a bit different. And so to answer your question, we have molecular chlorine like this, and then we have atomic chlorine. Atomic chlorine is usually thought of as chlorine gas. That's normally when people think of atomic chlorine, they're thinking of taking this diatomic chlorine and then splitting it apart. Either through violent collisions or some other way, and break the atoms apart. When you break the atoms apart, well, they're not that happy individually. And so atomic chlorine is much more reactive chemically than molecular chlorine. Molecular chlorine is more happy being paired. Atomic chlorine is going to be very unhappy by itself. And so that makes it chemically much more reactive. Okay, this is electrolysis of water, the setup in your book here. Let's see here. I think these came out in the PowerPoint, but let me just make sure. All right. When we're looking at the electrolysis of water, compounds can be separated into the elements by chemical separation techniques. One of the chemical separation techniques is you pass electric current through this. So this could be a source of fuel. What people are looking at is they're looking at using solar energy to separate water into hydrogen, air, and oxygen. Now, water contains hydrogen and oxygen. Is the hydrogen in water H or H2? The hydrogen in water. Is it H or H2? You would think it's H2 because it's called H2O. But when we think about H2, we're thinking about this. This is H2. It's hydrogen gas. Hydrogen gas is a very flammable gas. So if water contains H2, automatically I'm thinking, oh, it contains hydrogen gas. Watch out, it's going to be highly flammable. Is that correct? No. Is water highly flammable? No. Is it a gas? No. Maybe it traps? No. And so these hydrogens don't behave, even though they're two hydrogens. These two hydrogens are paired with each other. These two hydrogens are just paired with oxygen. So chemically it's quite a bit different than this. And so normally when we think about hydrogen and water, we think about H or H2. We think about H. How much H is in water? Well, there are two H's for every O. That's how much H is in water. But we don't say there's an H2 in water, because if we said there's an H2, we'd be automatically thinking diatomic hydrogen, molecular hydrogen. Does that make sense? And so we have to be careful about certain things. Now, in water, is there oxygen in water? Yes, there's oxygen in water. Is it O2? Does water trap O2 gas within itself? No. The oxygen in water is just O, right? Oxygen atoms. There's oxygen atoms in water. There are hydrogen atoms in water. We have one oxygen, two hydrogens. However, when we break this up into the elements, how do we break it up? We supply electric current, and that breaks it up, the voltage. And so we end up with hydrogen, the element hydrogen, and the element oxygen. When we're talking about elemental, what's the most stable form? Well, the most stable form for hydrogen is diatomic, most stable form for oxygen is diatomic. So this is why we end up splitting it into those by electrolysis. And you set up electrodes. Electrodes are just, pieces of metal, electrical conductivity. So one metal you push electrons onto, making it, electrons are what charge? Negatively charged. The other electrode, you suck electrons out. You suck electrons out from it, it makes a positive charge. So this is called electrodes because we can put a charge on them. This charge is called a voltage or an electric field. And if we get a high enough voltage, things can break down. So for example, a lightning bolt, air breaks down in a lightning bolt if you get a high enough voltage. Because over here, water can break down with a high enough voltage, and when it breaks down, you form hydrogen gas and oxygen gas. Not everything can break down like this in this particular fashion, but water can here. And so when we're thinking about names of elements, we're really careful about it. And so on the left, do you know what molecule that would be there? This carbon's usually represented as black, and oxygen is typically represented as red. So this is carbon 1, oxygen 1. It's a 1-to-1 ratio, which is CO. You guys know what CO is? Carbon monoxide. This is carbon monoxide. Now, when people are talking about the oxygen content of carbon monoxide, they're talking about O, right? Not O2. When I'm thinking about carbon, then it's a bit trickier because in this case, is there graphite that occurs in carbon monoxide? Is there diamond? Maybe that's diamond. No, it's neither. It's just carbon atoms, right? The carbon atoms in carbon monoxide. Whereas if we're talking about elemental carbon, that is solid carbon, then we have multiple forms of solid carbon. What are the forms of solid carbon, pure carbon? We have graphite, and we have diamond, and we have buckyball. Okay, but neither of those would be here. Over here, this is CO2. Now, some people think there's an O2 molecule, like oxygen. The oxygen we breathe, O2. Is there an O2 molecule in CO2? That way you won't asphyxiate yourself. We fill this room up with CO2 instead of O2, and we remove all the O2 out of this room. Can you survive? No, you can't survive. It's not an O2, right? This is 2 oxygens. This whites are typically hydrogens. Do you recognize this molecule? This is 1 carbon, 4 hydrogens, which is called CH4. CH4 you might recognize. CH4 you might have heard of before. What is CH4? Methane. It's methane gas. Let's see if we can figure out the last one. This one you might, or you might not. This is a carbon here with 3 hydrogens. So we call this CH3 because there are 3 hydrogens attached to it. And then we have an O and then an H. CH3OH. CH3OH is how to condense, this structure into a formula of CH3OH. What some people do is they combine the H's, and so they just say CH4O. But if you say CH4O, it makes it sound like there are 4 hydrogens bonded, like a methane, 4 hydrogens bonded to carbon, but that's not the case. And so sometimes we like to separate it. In this case, CH3OH, do you know what that's called? Yeah, this one's methane. This one is called methanol. Turns out this OH group is what we call an alcohol group. It's methanol. But you don't have to know that just yet. Let's look at the chemical formulas for these. What's the chemical formula for this? This one always looks like a little dog or something. But what do you think this one's called? Well, let's figure out it's C, it's carbon, with how many hydrogens? 3. So this is CH3, and then this carbon has how many hydrogens? Is this hydrogen bonded to this carbon? No, this one's bonded to the oxygen. So this is these are bonds. This is what the bonds are, kind of strong, and they hold the atoms together tightly. Chemical bonds rely on forces. What type of force is it, you know, that holds these atoms together? Is it the bonding force? It turns out, what type of force of nature holds these atoms together? It's odd, but, and we'll talk about it more when we get to bonding, but Coulombic forces, which we call electrostatic forces, hold the atoms together so tightly. And it's just positive and negative attractions, but you know, it's hard to see because these are not what we call ions here. So, but it is. It has to do with positive and negative attractions. In fact, all of chemistry relies on positive and negative attractions. That's it. And so chemistry is all just pretty much Coulomb's law. All of it. Anyway, getting back to this is CH3, C with 2 hydrogens, so we call it CH2, and then followed by an OH. So this is called CH3, CH2OH. We typically write it like this. CH3, CH2OH. This is what we call a condensed structural formula. Because we're taking that structure over there and condensing it into a formula. Versus a molecular formula. Take a look at this. This is the molecular formula here. C2H356H6O. This would be the molecular formula. It still, you know, has 2 carbon atoms. And then we got 6 hydrogens and 1 oxygen. So this is the formula. But what gives us more information? The molecular formula or the condensed structural formula? The condensed structural formula tells us a lot more about how things are arranged, you know. We're interested in both. Composition, right? Which both formulas tell us the composition. Both formulas tell us we got 2 carbons, 6 hydrogen, and 1 oxygen. But the condensed structural formula gives us some structural information as well. Whereas the molecular formula gives us no structural information. We'd have to sit there and try to figure it out. In fact, we run into a problem with this molecular formula. Because this particular molecular formula, we could arrange the atoms differently. If we arrange the atoms differently, then we come up with, you remember isotopes? Isotopes are what? Same element, different mass. There's something called an isomer. Have you ever heard of isomer? An isomer is the same formula, different structure. And so this particular formula might yield this structure, or it might yield a different structure. A different structure would be CH3OCH3. CH3OCH3 is called dimethyl ether. Its properties are totally different than this. You recognize this one? I told you about the OH here. A COH. When you see a carbon bonded to an oxygen bonded to hydrogen, you know what that's called? An alcohol type group. Yeah. It's a little bit more complicated because there could be other things that change it. But this one is an alcohol, and it's called ethanol. Ethanol. Meth, you know what meth refers to? Meth refers to 1 carbon atom. If you have F, that refers to 2 carbon atoms. So the difference between methanol and ethanol is that methanol has 1 carbon, ethanol has 2 carbons. If we have 3 carbons, do you know what we call it? 3 carbons. We call it prop. And so we have propanol. Propanol is a 3 carbon alcohol. Butanol is a 4 carbon alcohol. Pentanol is a 5 carbon. Hexanol, 6. Hept, H-E-P-T, is 7. Oct, 8. Yeah. Nonol is 9 carbons, and decanol would be 10 carbons. So this is ethanol here. Now this is dimethyl ether here. Meth is 1 carbon, so we have these 2. So this is called dimethyl ether. This dimethyl ether and ethanol have the same formula: 2 carbons, 6 hydrogens, 1 oxygen. However, their properties are totally different. You don't want to drink this stuff. Dimethyl ether will kill you, I think. Methanol will kill you too. Don't drink methanol. Methanol is called wood alcohol. Ethanol is called grain alcohol. Grain alcohol you could survive. I mean, it's still in too large of quantities. Be potentially toxic, but methanol is highly toxic. Methanol, is it an urban myth or legend that drinking alcohol will make you blind? Have you ever heard that? Drinking alcohol will make you blind? Yeah, drinking methanol will make you blind permanently. And people have been blinded by drinking methanol. So don't drink. Every year there are cases where people have gone blind and died. They don't really publish them in the news that much. In the chemistry news, they do. Chemical news, they'll say, 8 people died, something like that, consuming methanol. Anyway, over here, this is what would we call it? H2O, CH2O. Have you ever heard of CH2O? Now, the H2 is not hydrogen gas. CH2O is called methanal. Methanal has a common name. There are a lot of different names that we give things. A lot of them are just common names. Like methanol is called formaldehyde. You don't want to drink formaldehyde. And so ethanol is also called ethyl alcohol, grain alcohol, sugar alcohol. And this, when we see something like this, this is what we call a ketone. This is a ketone too. Ketone is a carbon with an oxygen stuck on it. If there's a hydrogen there, then you think it's an alcohol, but it's a ketone. This one is, this is one, can you see how many carbons this is? 3 carbons. 3 carbons gets the prefix, let's see, meth is 1, F is 2, what was 3? Pro. Yeah, this one's called propanone. Propanone. Propanone has a common name because it's a very common chemical, propanone. This one is called acetone. Acetone is AKA propanone. Actually, let me see if I have these figures. Greatest. Well, what gas is that? You probably can tell based on the tank. What is that? Helium. And so the element helium is just He. This gas. Propane. Do you know what propane? How many carbons propane has? 3. 3 carbons. Propane looks like this. There's a 1, 2, 3 carbons bonded. The first carbon has 3 hydrogens. The second carbon has 2 hydrogens, and the third carbon has 3 hydrogens. So propane has the formula CH3, CH2, CH3, or C3H358, C3H8. Propane normally is a gas. This form of molecule. So we can tell that it's not propane because we have these molecules here rather than this. And then, in a propane tank, propane's actually a liquid inside the tank. Outside, it's a gas. The heck is that? This does not look, well, what is that? Is that lithium? That looks like an awful sample of lithium. You know why?
Is lithium like yellow?
Lithium is metal, and so this looks like a highly corroded sample of lithium. I don't know why they chose that picture because it looking at that. But lithium is going to be a lattice. So let's take a look at a better shot of some fresh lithium. Lithium is subject to corrosion. I mean, it's a metal that's very easily corroded. And so you have to get a really fresh surface of lithium. Let's see if we can find a fresh surface of lithium. Here. And so do you see all the surface corrosion here? It rapidly corrodes in air. You have to watch out because this lithium can catch on fire, if you're not careful. And so if you cut it, it's easy to cut. Lithium, like sodium, like potassium, are very soft metals. They're, in other words, the bonds that hold the atoms together are kind of weak, making them soft, easy to cut. And so we can slice this. When we slice this, you can see some fresh lithium. It has more metallic luster there. So I don't know why they didn't show something a little bit better than this because, well, maybe, I don't know. At first I was thinking it's charcoal. So I was thinking they're trying to show us some charcoal. Anyway, lithium packs together as a lattice. So when people talk about lithium, they're talking about solid lithium. Or they could be talking about lithium with a positive charge. And so if they're talking about the element lithium, it's lithium solid. Or lithium metal, if they're talking about lithium metal, it's lithium solid like this. So we just, even though you might think this is molecule, it's not because there's no discrete ending. Molecules will definitely have an end, like H2O, that's it. But something like lithium, you can extend on 3 dimensions, infinite. You can just get bigger and bigger. It's a lattice. And so the easiest is to just draw the simplest. The simplest is Li. The same goes for something like sodium chloride. If we go back and take a look at the sodium chloride lattice, we got a lot of sodiums there. Should we count them up and then count all the chlorides? No. What they do is they just take the simplest. The simplest is 1 sodium for every chloride. So that's our chlorine. 1 sodium, 1 chlorine is NaCl. Well, the same thing with lithium. We call that the empirical formula. The empirical formula is the simplest ratio. Let's get to lithium. Of course, for hydrogen gas, we've talked about this a bunch. Hydrogen gas, like lithium metal, is highly flammable too, so you have to be careful with hydrogen and lithium, all those. Very flammable. So here, flammable gas, no smoke, no open flame. No open flame. Do you need an open flame to ignite hydrogen? Do you need a flame to ignite things? You don't need a flame. You just need a hot surface, right? All you need is enough kinetic energy transfer, enough heat transfer. And so just a hot surface can ignite many substances. Well, anyway, we talked about the 7 diatomics. Memorize that. Okay, let's skip the elements now. We're going to go to compounds. Okay, now we have different types of compounds that we deal with. So let's take a look at the types of compounds first. And we'll get into naming these. Okay, the first type of compounds we'll talk about are molecular compounds. Molecular compounds form molecules. Not all compounds form molecules. Can you name a compound that does not form molecules? How about quartz? SiO2, that's a compound. Does that form molecules? Or lattice? Forms a lattice. So how do we know if a compound forms molecules or forms a lattice? How do you know that?
Go with the structure.
Yeah, if we can look at the structure, if the structure is given, then we can tell easily, right? Tell easily. So types of compounds would be like molecular, CO2. CO2 is molecular. It's carbon dioxide. N2O. N2O is laughing gas. CO2 gas. N2O is gas. But if we go to SiO2, SiO2 is quartz. Is quartz a molecular compound? No. SiO2 is a solid. So sometimes the state can give it away, sometimes it don't. Sometimes you know. This is not a molecular. So SiO2 is a lattice structure. Okay, so what we have here is this: compounds that are made from two nonmetals. Okay, two nonmetals, we know the periodic table is divided into metals and nonmetals. So two nonmetals would be, let's, in the yellow region here, in which carbon is a nonmetal, oxygen is a nonmetal, nitrogen is a nonmetal, oxygen is a nonmetal, molecular. How about silicon? Silicon is a metalloid. Oxygen is a nonmetal. Metalloid. And so it appears that, well, a metalloid is not going to form molecules. And so the situation is this: typically two or more nonmetals bonded together will form molecules. There are exceptions. All right, let's look at, what do you think, arsenic? Arsenic combined with oxygen. Do you think that's going to be a lattice or molecular type structure? Arsenic and oxygen. Well, do you know the symbol for arsenic? AS. So if we have a compound made of arsenic and oxygen, do you think that would be a lattice type structure or molecular type structure? Probably a lattice, but there are exceptions, so you just say probably a lattice. But might not be. So there's a little bit of uncertainty. How about selenium and oxygen? That is likely to be a molecular. How about bromine and oxygen? Molecular. So there's a little bit of uncertainty here. since there are exceptions, we cannot be 100% certain. So the best thing to do is look it up and see. Obviously, it'd be nice to be able to predict that without having to look it up, etc. All right, if it's a molecular compounds have their own naming. And so, so let's look at naming. All right, now we're going to look at molecular compounds in different categories. Two element, which we call binary molecular compounds. Two element would be, an example would be carbon monoxide. However, if we had something like this, let's go with CH3OH. Is that binary? CH3OH. This is not binary. No. Is that binary? How about that? Is that binary? Yeah, that's binary. And so these are okay. Two element binary, this is how we name them. So let's take a look. The name of a binary molecular compound is two words. The first word is the element that appears first in the chemical formula. So, carbon, carbon, carbon. The prefix indicates the number of atoms. And so what we'll do is we'll put a prefix in front of the name of it. So we should call this monocarbon monoxide, but mono is often not used. You know, we'll just call it carbon monoxide for sure. Mono. However, this one, we wouldn't just call this nitrogen monoxide, right? Because we might get confused. This one, we definitely need a prefix. Yeah, this would be called dinitrogen monoxide, also known as laughing gas. The second word, the element that appears second, oxygen, except we changed the ending. We changed the ending to IDE. So rather than calling it oxygen, we call it oxide. Carbon monoxide. Includes a prefix to indicate. Two compounds that are always called by their traditional names of H2O, water, and NH3, which is ammonia. That's not accurate. You know, I was looking in a chemistry catalog. It was a European manufacturer. I was looking in the European catalog for some ammonia. I needed to buy some ammonia. I couldn't find ammonia, and I couldn't believe it because this is a big chemical manufacturer, and if they don't have ammonia, it really surprised me. And then I realized they didn't call it ammonia. You know what they called it? They called it by this naming system. They called it, okay, so the first element would be called nitrogen or mononitrogen, but we usually on the first one we skip the mono, so it'd just be nitrogen, and then how many hydrogens? Tri, but rather than calling it trihydrogen, which we wouldn't call it trihydrogen, we'd call it trihydronide, but trihydronide sounds funny, so they shortened the name to trihydride, and so they called it nitrogen trihydride. And so, that's it. Now, This one, how would you name this? Hydrogen monoxide? Yeah, except in this case, hydrogen, if we just called it hydrogen, it would refer to one hydrogen. So we should call this dihydrogen monoxide.
They should be called oxide instead of monoxide, or
In this case, monoxide.
Monoxide.
Yeah. The second element, we usually put mono on that. And so, dihydrogen monoxide is just water. But who wants to call it dihydrogen monoxide? Does anybody call it dihydrogen monoxide? Have you heard about this? The DHMO hoax? Did you hear about that? These guys got a city council to come up with some declaration banning the chemical DHMO. So there's some official document banning the dihydrogen monoxide. Everything they said was true because dihydrogen monoxide is potentially lethal, right? Drown. Because of that hazard, the city decided to ban it. So, well, anyway, where was it? So these are things. A major component of acid rain, greenhouse effect, severe burn, erosion, corrosion, etc. But, well, anyway, that's it. So let's look at some examples. Before we look at some examples, let's look at some prefixes. So, mono, 1, di, 2, tri, 3. This is different than the counting the carbons. You have to know some prefix systems like meth, eth, prop, mono, di, tri. 4 is tetra. 5 penta, hexa, hepta, octa, nona, deca. These are similar to what we see for carbon atoms. It's just for carbon we just have meth, eth, prop, bute, and then the rest are the same: penta, hexa, hepta, octa, nona. Well, these are the prefixes for naming the number. And so, dinitrogen pentasulfide. What's the formula for dinitrogen pentasulfide? N2S5. N2S5. That's good. Do you predict that to be a molecular or a lattice? It's molecular. How about this one? Dinitrogen pentoxide. N2O5, it's also molecular. What would this be called? I409. Tetraiodine or iodine, nonoxide. And PF5, phosphorus, pentafluoride. So let's check your answers here. N2S5, N2O5, tetraiodine, nonoxide. Phosphorus pentafluoride. Now, nona, look at, they said no oxide. No side. Let's look at the prefix again. What's the prefix? Nona. And so it should be nona oxide. Double vowel. It would go A-O. Nona oxide. But typically what happens is it will drop the double vowel. Is it carbon monoxide or is it carbon monoxide? It's carbon monoxide, so they've dropped one of the O's. And is it nona oxide or is it nonoxide? It's nonoxide. They dropped the A. Just to make it sound better.
So did we ever stay like that?
Depends. For nonoxide, no. What about the 3-element compounds and higher? For what we call ternary compounds, you know, binary, ternary, quaternary, I don't know what after that, but for those, there are a whole bunch of complex rules for naming those. And so we're only going to name binary, and that's it. And so when it comes to this one, when it comes to something more complicated, let's say we have something like OPCl5. We don't use the rules for this. I mean, this one would not be called, this is not called oxygen, phosphorus, monophosphorus. Pentachloride. That's not what it's called. Note the rules only work for binary. Okay, the rules only work for binary. Anything higher than binary, we aren't going to cover. Unless it's a special case. That's it. Okay, let's let's take a break right now for a little bit. And we'll start up again in about 10 minutes. Take a break.